Hi there, you're in the lab with your mate JJ. Today is Maxitronix Day. Today we'll be doing project number 13 from the Maxitronix Sensor Robot 20, which we affectionately call our 20-in-1. The project for today will be a ferromagnetic substance detector. So let's jump on the computer and have a look at the instructions. Then we'll pop over to the booth and we'll put it together. And once that's done, we'll bring it over to the bench and we'll have a look at it underneath the thermal cam and the oscilloscope and so on. So yeah, let's jump on the computer. Alright, here we are on the computer. So just going to fire up our web browser here and we'll start a new session. And we'll just synchronize so that we've got everything we're looking for. There it is, project 13 of 20. Let's fire that up. Alright. This is the Maxitronix 20-in-1. Let's scroll down the bottom here and let's open this one up. Can you see that? Yes, you can. Alright. This is the ferromagnetic substance detector. What it does: your sensor robot can help you to find out if a piece of metal or some other material can be magnetic or not. Again, your robot uses the reed switch as its sensor, but this time the buzzer sounds if the material is iron based. Other materials that sound the buzzer are nickel, cobalt, and certain types of steel. Check some common things around your home. For example, test a sewing needle. Some needles are made of a special non-magnetic steel. Others are highly magnetic. Try to get a Canadian 5-cent piece. Many older ones are magnetic because they are made with a high percentage of nickel. Turn the control on. The buzzer sounds. Bring the bar magnet near the reed switch until the buzzer stops. Place the unknown material between the bar magnet and the reed switch. Refer to the illustration. If the material is one that can be magnetized, the buzzer sounds again. Otherwise, you hear no sound. How it works: if the reed switch is closed, the voltage between the base of the emitter of Q5 stays at 0 volts. If it's closed, it's at 0 volts because the power is running through this resistor, through the switch down to here, and there's no voltage on the base of Q5. And Q5 remains off. If Q5 remains off, so does Q6. Q6 is here. Okay? And the buzzer does not sound. But if the switch opens, current flows to the base of Q5 from the battery through a 3.9k ohm resistor and turns on Q5. This also lets Q6 turn on. As a result, the output of the astable multivibrator, this is the astable multivibrator, these two, Q3 and Q4, these create the oscillation that produces the tone, which is amplified by this transistor, and in fact controlled by this transistor, essentially. So this lets Q6 turn on as well. As a result, the output of the astable multivibrator goes to the base of Q6 and the buzzer sounds. Okay. If the material is magnetic, the bar magnet's lines of force pass through the material and are absorbed. Because of this absorption, the power of the bar magnet does not affect the reed. As a result, the reeds remain open and the switch is open. If the material is non-magnetic, the bar magnet acts upon the reeds, closes the switch, and the buzzer remains silent. Alright, so we'll have a play with that when we're ready. But now let's pop over to the booth and let's wire this thing up. here in the booth. So the first thing to do is take out the wires from the previous job, so let's do that first. Alright, so now we're ready to wire up our new project. Let's do that together. Alright, so that's all wired together now. So let's pop over to the bench and see if it works. Here on the bench. So the first thing we need to do is organize for some power. Now I like to power it off the bench supply rather than the battery so that we can see how much power is being used. So let's just put this on I'm pretty sure that's negative. Yep, negative and positive. Alright, now I've got it set at 9 volts. So let's see what happens if we we'll turn that off to start with. Put the power on. Okay, the power is at 9 volts. Turn the switch. And now we're going to need our magnet for this test. So there's a magnet here. Let me just pop that out. There's one magnet and there's the other magnet. Alright, so that back there, we've got our wedge to try and keep the glare off. So far that seems to be working okay. Now, how are we doing? No, it's a bit glare there, no glare. Alright, now it did say to move the magnet, so we put it on. There we go. Okay. Now, what we want to do is we want to use something that is magnetic. And if we put it between and it beeps, that means that it is magnetic. Cool. So this, my professional opening tool, is magnetic. We can tell because we put it there. Oh, no. Ah, I'm a bit confused. This is magnetic. So we put that there. We move it back until it starts to beep. Oh, it's not behaving the way I thought it would. So perhaps, I don't know. What about these? These will be magnetic. So it says turn the control on. The buzzer sounds. Bring the bar magnet near the switch until the buzzer stops. Okay. Okay. Place the unknown material between the bar magnet and the reed switch. Okay. Just trying to pull this out here. There we go. Alright, so it says the buzzer sounds. Bring the bar magnet near the switch until the buzzer stops. There. Alright. Place the unknown material between the bar magnet and the switch. If the material is one that can be magnetized, the buzzer sounds again. Okay. That's true. Alright. So I think the problem with the professional spudger is that it's too thin. Do you see it's very thin? so it doesn't. Oh, there we go. If you get enough of it in there. What's happening now? I'm a bit confused. Have I damaged the switch? No, not sure what happened there. So you place it near the thing. Alright, bring it until it stops. There we go. Yep, okay. Now let's test some material that's not magnetic. What about this? This is the little bit of plastic. It's not magnetic. So we bring it near, we bring it back, and then we put that in there and it should make no effect. Yeah, of course. And yeah, I think that's everything. Now I suppose that we do have in this circuit, we have the astable multivibrator, which is this part of the circuit here on the bottom left. Now that produces the oscillation that goes through Q6 that provides the tone on the buzzer. So that's an oscillator, and anything that oscillates we can look at with the oscilloscope. So let me fire up the oscilloscope and we'll have a look at the signal that comes out of the astable multivibrator. The other thing that we'll do is we'll turn on our UNI-T. And the UNI-T thermal cam, in fact. So we can use the thermal cam to have a look at the temperature, at how the circuit behaves under temperature. So I'll be back in a second when I've got the thermal cam operational. So give me just 2 seconds. I've just moved the whole unit across a little bit. I'm trying to get all of the transistors in view of the thermal cam. So that's the reason for that. What I wanted to do with you just quickly is have a look at this. Now, I made this recently. It's 3 LEDs with attached resistors, and also I've got this buzzer with an attached potentiometer, and what I want to do is just get myself some cables here. Now we're going to need to do a bit of wire stripping, so here's a wire stripper. Now the first thing I'm going to do is just chop off the bit that we don't need. Whoop. There we go. So don't need those anymore. Put them in the scrap. Now what do you reckon this is? I reckon this is 24 gauge, I reckon. So let's just put that there. Now this is stranded wire and it's not tinned, so we might just fire up the old soldering iron. I'll just put that on now. The soldering iron on, and I'll give that a bit more length there. Alright, so a little bit of scraps. Now I just want to twist these together and then maybe just tin them a little bit. These will be for inserting into the spring terminals, so that we can what I want to do is I want to wire in this buzzer here and see if I can use the potentiometer as a volume control. That's one thing that I want to do. And the other thing I want to do is use the audio signal as a pulse width modulated input into one of these LEDs, so that we can see the feedback instead of hear it, because I don't like that noise when I'm trying to talk to you. So here's a little bit of solder on the thing. There we go. So that's just a little bit of tinning on the end there, and we'll do the same on the black. You know, I do have a solder pot, and I haven't had much experience with that yet, so that might have been a good excuse to try out the solder pot, but it really is only just a little bit of tinning that we're doing here, so no big deal. I'm not sure how much that helps. Anyway, that's done. I'll turn the soldering iron back off. So we've got some tinned wires here now. This is our thing. So the first thing I thought we might try is the speaker here. So instead of wiring this into the buzzer, let's just unplug this one. So we'll take him out and we'll plug him on. Alright, just plug him in there. And then we'll put this one in here. Alright, and let's see what we've managed to achieve. Okay, so that tone is now coming out of the different speaker. I believe it is anyway. Yeah, and because we've got the potentiometer attached, we should be able to stick our screwdriver in there and turn it down. Yeah. Okay. So that's I don't know if you can hear that. I certainly can, and it's a lot less offensive than it was. So that's good. Now the other thing that we'll try is just putting this onto an LED. So let's use green. Hopefully we don't fry anything. Let's see what happens. So if we turn that on, okay, nothing, which is probably just polarity. Let me try the other way around. I don't think we're sending enough juice to fry these things, so this should probably work. Yeah, it works. Great. Okay, so now we've got a green light instead of an audible tone. So we should be able to turn that on, and if we bring our magnet into the picture again, it should turn the light off. Yep, light on, light off. Great. Look, I'm just going to go and make a coffee, and I'll be back, and then we'll have a look at the tone on the scope. I'm back, and I've got my coffee. I find all this talking really dries my mouth out. So, where are we? Well, we've switched our tone out for for the little LED. So now we've got a green LED, which we can control with this reed switch, which is cool. We've done all of the experiments with the material that I was really interested in doing. We tested something that was magnetic. Two things, in fact. We showed that it didn't work with a non-magnetic material like plastic. So the next thing that I want to show you is the thermal behavior, and particularly I want to show that the bits will heat up. What am I trying to say? Okay, well, first of all, let's just throw you over to the thermal can, okay? Now you can see the transistors there at the bottom left. So what I'm going to try and do is bring them all the way across, so they're just almost out of the scene, but they're still there. Now, what's that? That looks like a thumbprint to me. So that heat signature down the bottom left, that's just where I've touched the board and it got hot. Now we can see the two transistors. Now the thing to know about these transistors, the two there on the bottom left, is that they're operating right now. So that's part of the astable multivibrator. In fact, let's throw you over to hang on a sec. I'll be back in 1 second with the oscilloscope on the screen. So give me 2 seconds. All right. So here we are with the scope. Now I just need to put it somewhere where we can see. So let me throw you back over to the other view for a second, and let's just have a look here on the I might just turn that off for a second. Now if we have a look here, the input to Q6 on the base, that's where the output of our astable multivibrator goes. So on pin 64, which is the base of Q6, that's where we should find our oscillating signal that provides the tone that drives the board. So we're looking for pin 64, which is here. And then we want to connect that through to ground. So we need something that's on ground and that's near here. So 48, where's 48? 48's over here. Okay, cool. Well, is that long enough? It's not long enough. We need something. What I'll do, I'll just get a little wire. Alright, so 48 here is the emitter of Q4. It's on pin 48, so that's 48 over here. And we're going to send it across as the ground signal for the probe, and then we're going to hook the probe up to the base of Q6, which is where our astable multivibrator tone is going. So we'll just put that on there. Now let's auto calibrate the scope, and then I'll throw you back over. You can see the scope there up the top now, and we can move it up and down and move it a bit. So there we go. So that's the sig now. Just give me 2 seconds. I'm going to play with my oscilloscope. Sorry, I might as well play with my oscilloscope with you as well. So what we're trying to do, I found display. I press display. It pops up this menu. And then I want show scale, and we put that on. and then it showed us the scale along the side there. So does it tell us the frequency? Alright, there we go. So it is actually bottoming out at 0 volts, and it goes all the way up to a little under 1 volt. And the frequency, how do we show the frequency? Measure and add, and what do we want? Frequency, and then yeah, that's done. So there it is, the frequency. It's 1.56 kilohertz. So that's the tone that you hear when the when the buzzer sounds. Of course, at the moment, we're actually just sending that tone or that signal into the LED, and it'll act as a pulse width modulated voltage, which is enough to drive our resistor. Now, so we've had a look at the output of this astable multivibrator. So the other thing I want to do now is throw you back over to our thermal cam, which is here, and then just talk a little bit about what's going on with that. So you can see in the bottom left there, here and here, two transistors that are obviously conducting some energy, because you can see them getting hot. Now the other thing that's getting hot here is this. Now that is the 3.9 kilo ohm resistor, which is actually here. Do you see? That's the 3.9 kilogram, kilo ohm. It's a kilo ohm, a 3.9 kilo ohm resistor, which is actually going through the through the reed switch, because the reed switch is closed. Oh, it must be closed. Yeah, it's closed because the magnet's there. Now, if we take the magnet away, the LED goes on up here, and the resistor will start to cool down because it's not going straight through to ground anymore. It is still conducting those, so some amount of energy will be going into the base of Q5. So what I'm going to do, actually, I'm going to break out the old multimeter. So just give me a second while I set that up. Alright, I've got my old multimeter here, and I'm just going to put it on milliamps, or microamps even. Let's put it on microamps. And what I want to see is how much current is going into the base of Q5. Now, if you remember from our schematic, Q5 is the transistor which controls Q6, which is the amplifier for the for the astable multivibrator for the tone. So at the base of Q5, we've got energy coming out of pin 54 and going into pin 61. So we want to take 54, where is that? 54 is here, and 61 is there. Okay, great, that's very convenient. Let's take out the now I'm not sure which side's which. What did we say? Was it 54 and 61? So just putting those in there. Okay, that's so it's 2000 Okay, so 2.14 milliamps, which is actually quite a bit of juice, isn't it? Now that's when the switch is open. So let's see what happens when we close the switch. Okay, it draws more current in that situation. So when the switch is open, there's 2.13 milliamps, and when the switch is closed, there's 2.33 milliamps. So not a huge amount of difference, which just goes to show you actually that this circuit is kind of inefficient. It's burning through a few milliamps of juice in either configuration, and it's kind of negligible. I mean, it's 0.2 of a milliamp, which is what 200 microamps is the difference between being closed and being open. So yes, interesting. But of course, when it is closed, that is when it burns more juice. So when it's open, the energy is if it's open, the energy flows into the base of Q5, and that's when we see the 2.13 draw. And then when it's closed, it doesn't flow through here anymore, it flows through here. Is that right? Is that right? Is that what I want to see? Okay, I'm going to try measuring between 0.39 and 53. So let's set that up together. Why don't we do that? Take that out and put that back together as it was. Just putting that back into pin 54 there. Now, I want to see in between pin 53, which is here, and where's 39? Alright. So I'm going to take this one here out, and then I'm going to connect this between 53 and 49. Alright, and we're seeing the same thing that we saw earlier. Yep, it's the same. Alright. So what we did then was we showed that the energy flowing between 0.39 and 53 turns out to be the same as what flows between 54 and 61. Fascinating. So there you go. Alright, now is there anything more to show you? Yes, just the thermal characteristics when the system's on. So we want to see the transistors, which are over here, are getting hot. So those should start to warm up now, and you can you see them getting warmer? It just got a bit warmer there. So those transistors get warmer when the light is on, and the the output is active. When we put the switch in, it turns them off, and those will start to cool down now though. But there's a fair bit of lag on the thermals, so you won't expect to see it. But you can see those transistors in the bottom left over here, they're bright red because they're operating all the time. That's the multi-vibrator, which of course you can see here still on the what am I trying to point at? That, yeah, on the oscilloscope. So that's our 1.5 kilohertz frequency. Okay, that's everything. I think I'm gonna flip you over to the farewell cam, and we're gonna wrap up. And that's a wrap. What a great, exciting experiment. I really enjoyed that one. That was cool. So we got to use the thermal cam to have a look at the energy flowing through our transistors. We saw the astable multi-vibrator getting hot because it's always there operating, regardless of whether the amplifier allows the tone out or not. We saw the right side controlling transistors get a bit warmer when they were in use. We used our new soundboard with the potentiometer to bring the tone down so it's not so loud. That's good that works. I'll use that again in future projects. We also switched it over to use the LED as an option instead of the buzzer, so that just makes less noise, and it's just a bit easier to use. So I'm very pleased to have that little scrap of circuit board there with those LEDs and that buzzer on it. I'll definitely be using that again in the future. Of course, we put the scope in. We had a look at the 1.5 kilohertz signal coming out of the astable multi-vibrator, which produces the tone. We got the LED working on the pulse width modulation from the tone. And we even did a little bit of soldering to tin up those tips. So yes, what a great experiment. Very happy about that one. Oh, of course, the ferromagnetic experiments also worked. We put the ferromagnetic material in, and it affected the reed switch, which is what it was supposed to do. So that was pretty cool. Yes, all in all, very happy. I have to say this is probably my most favorite experiment that we've done so far. So I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe. Hi again. Look, I just wanted to record a little bit of an add-on because I was perhaps looking at the wrong thing earlier. I was interested in knowing how much current was being consumed by the circuit in its two different states. And we had a look, and we saw that it was drawing a couple of milliamps. But that perhaps missed the point. What I've done here is I've put the multimeter into voltage mode, and I've put the probes across the base and the emitter of Q5, which is the main switch in the application. And what I want to show you is that it's not the current that causes the transistor to go. It's the voltage. So when we've got this down here, the switch is closed, and when the switch is closed, the energy all runs straight through the switch, and it goes straight to ground, and it won't activate the transistor. But if we move the switch away, the magnet away, the switch opens, and then the voltage is available on the base, and you can see that here. The base now has 0.76, so nearly 0.8 volts. and obviously this triggers around half a volt, 0.6 of a volt, 0.7 of a volt. So that's enough voltage there now to activate the transistor. Whereas if we put that there, the voltage gets sucked down to like what 1 millivolt, which is not enough to drive the transistor. So earlier when I was looking at the current, I was interested in the efficiency of the system in its default state, and if it's always drawing a few milliamps, obviously that will wear out a battery over time. So that was why I was interested in the difference between the on state and the off state, which we noticed wasn't very much, about 0.2 of a milliamp, I think it was. Anyway, as we can see here, it's the voltage at the base of the transistor that causes the transistor to activate. So and you can see that's 0.76 volts is enough to do that in this circuit. So I just wanted to add that little bit of clarity. I suppose the other thing, since I'm here and trying to confess about the mistakes I made when I made this video, which I'm still very happy with, I really learned a lot in this video. This is the astable multi-vibrator that we looked at earlier with the scope at the 1.5 kilohertz signal. And perhaps I didn't explain well enough actually what this circuit does. This is the guts of the schematic here, and it's called an astable multi-vibrator, and basically coming out here at this 10K resistor is a 1.5 kilohertz square wave. Now, as we saw on the scope, it's not exactly perfectly clear, but it's basically a 1.5 kilohertz signal, and that produces the tone. So when this Q6 transistor is open, when Q5 allows it to, then the signal will appear on the buzzer, and the signal is the tone. So yeah, that's what the astable multi-vibrator does. And these are the transistors in the bottom left of the screen that we saw were hot. They're always hot because this tone is always being generated. That we don't turn the oscillator on and off when we need it. It's just always there oscillating, and we just route it through to the output when we want it to. Otherwise, we just leave it there oscillating and not going through to the output. So hopefully those two things just clear up any confusion there, and we're all learning electronics together. So I hope you're having a wonderful day, and I'll see you in the next video.